and welcome to the final day of the 24-day extravaganza of physics. And what I've got here is a question on electric fields, okay? So it says here, question 24, define the electric field strength at a point in an electric field. So the definition, of course, of any electric field, may it be radial or uniform, of course, is E equals F over Q. So electric field strength is force per unit charge. Okay, now this second part is important. So there's 2 marks. Normally when you get a defined question, there's 2 marks. There's normally a caveat. Like Hooke's law. Hooke's law is force is proportional to an extension up until the elastic limit. So for this one, it's force per unit charge. And it's important because, of course, field strength has a direction. Okay, so it's force per unit charge on a positive test charge at a point in the field, okay? So this is important that the field strength at a point is dictated, the direction of that field and that the field, so the actual value for the magnitude of the field strength is source per unit charge, okay? But the direction of that field is dictated by the direction a positive charge would go. So if it is a positive, so remember, electric fields go from positive to negative, okay? And if I stuck a positive charge there, it would want to have a force going away from it. And of course, if it was a negative charge, so it would want to go towards it. So the direction of the field line is actually dictated by where a positive charge would go. So in the case if this was a positive charge here, if I had a positive charge here, it would go that way. And that's why the field lines from a positive charge go out like that. Whereas in a negative charge, they go in like that. Okay, because it's the direction thing. So this one here, force per unit charge on a positive test charge at a point in the field. That is the second caveat that you need to remember. Just grabbing the mark scheme up for you guys, just so you can actually see what the mark scheme looks like. So it says a force per unit charge, which is exactly what it is. So if you wrote that, you would have nailed that straight away. But it says on a positive test charge at that point. Okay, so this one here is actually mentioning that you're talking about the direction. Why is the direction dictated by this positive test charge here? Okay, so the next point here shows a point of 46 microcoulombs placed at 120 point charge of 46 microcoulombs here, or placed 120 meters from charge Q. The position P is the point where the field strength, the resultant field strength of P is 0. So it means that the field strength from this and the field strength from this are 0. There is no field strength at that point, okay? So field strength actually, since field strength is E equals F over Q, having a bit of a mare there. There you go. E equals F over Q. That means at that point, for there to be 0 field strength, there must be 0 resultant force. So it means that whatever this point is that if I put a positive charge there, it will be repelled by this one this way. So this is the force from the 46, okay? Which means that if I put a positive charge there, it must be also being repelled from the charge at Q, because resultantly the force is 0, which means that the resultant field strength would be 0 at that point. So not only do we know this charge is positive, okay, which is really useful for us in a minute, but we do know that the resultant force at that point was 0. There are many ways of doing this. The easiest way, of course, if you know that resultant field strength is 0, you know that the field strength from this charge at this point must be exactly the same as the field strength from this charge at this point. Okay, so this is 120, that is 66. If you have some missing values like that, I do this with moments too. Take them away, so that's going to be 54 millimeters. Okay, so field strength in a radial field is 1 over 4 pi epsilon naught Q over R squared. So let's find the field strength for the 46 microcoulomb. So it's going to be 1 over 4 pi epsilon naught is 8.99 times 10 to the 9 times by the charge, which is 46 times 10 to the minus 6, all over 54 times 10 to the minus 3 squared. Okay, so 46 times 10 to the minus 6 divided by 54 times 10 to the minus 3 squared times by 8.99 times 10 to the 9, I get quite a big field strength of 141.8 times 10 to the 6 newtons per Coulomb, okay? And it means that this charge here must also have that same field strength, but it's going in the opposite direction, okay? Which makes sense because the field lines for this one would be going this way. And since we've deduced this one is also positive, the field lines for this one would also be going outwards. So the field is going in the opposite direction, okay? So now I know that my field strength is this. I'm going to use the same formula. So I've got 141.8 times 10 to the 6 equals 1 over 4 pi epsilon naught, so 8.99 times 10 to the 9 times by Q over 66 times 10 to the minus 3 squared. So manipulating that, so divided by 8.99 times 10 to the 9 is that, and then multiplying that by 66 times 10 to the minus 3 squared. And I get an answer, oh, no, that's not right. So 141.8 times 10 to the 6 divided by 8.99 times 10 to the 9, and then times by 66 times 10 to the minus 3 this time. Sorry, I made a mistake there. They go squared, and I get an answer of 6.8 or 6.87 times 10 to the minus 5. So 6.87 times 10 to the minus 5, which makes a bit of sense because it should be slightly bigger than this here. So let's check my answers here. So this has got 6.9. I've got 6.87. There you go. Rounding must be correct. So it doesn't say about significant figures, so they will allow me to have that there. So 6.87 times 10 to the minus 5. It makes sense. It's a bigger charge than this one here, and it's further away, which means that its field is much stronger in general. Okay. So 3 marks. One for actually, if you actually look at where the marks for this one is, you get 1 mark for realizing that the field strength due to Q is equal to the field strength 1 doing the maths, 1 for the answer, okay? So the fact that I've clearly gone, cool, I've done that, even labelled it up here, set it equal here, and got the answer there, I would have got my 3 marks, okay? Now, I hate these questions because I want to do calculation, and it says explain without calculation whether work must be done, and this is a trick. So we normally talk about, when we're talking about potential and work, we talk about it being removed from the field, not the other way. So explain calculation whether net work must be done in moving a proton from infinity to that position, okay? So if I was taking it outside of the field and I was trying to place a proton there, would I have to do work? Would I have to actually do work to put a proton there? And the answer is yes, of course you would. Okay, this is where it's really cheeky because it says infinity to position. So what you're doing is you're taking that proton outside of the field and you're pushing it into that field. Okay, the answer is yes. Work must be done. And of course, it's an explain question, so you need to say because the potential at P will be positive. Okay, so the potential at P would be positive because you would have remember, where potentials, you add them together, you've got the potential of Q plus the potential of the 46, okay? And since they're both positive charges, okay, because we worked that out before, since they are both positive charges, they will have a potential at that point. Just because something has 0 field strength at that point does not mean there is 0 potential at the point, okay? Field strength is directly proportional to 1 over r squared, and potential is proportional to 1 over r. So they decay at different rates. Therefore, even though there is 0 potential, 0 field strength there is still work to be done to move something back or forth in that field. Okay, so yes, work must be done because the potential of P would be positive. It means when moving a positive charge like a proton, you would have to do work basically to overcome the repulsion. Moving from infinity to P, okay? Because normally, if I had a proton and I put it at that point, the field would do all the work for me and boot it out. What I'm trying to do is I'm trying to get from outside of that field, I'm trying to take my proton and I'm trying to push it into that position. And all along the way, I'm being repelled. So I actually have to put energy in to put it to that position to combat the fact that the field is going to try and repel me out. Okay, so there's no, I've not done any calculation here, which is what they're trying to do is to make sure that you don't work out what the potential is at that point and then work out the energy. That's what they're trying to get you, not to get you to do. They're trying to get you to underlie the physics. So if you actually look at the work here, work must be done on the positive proton because P is a positive potential, or work must be done due to the repulsive forces and the potential infinity is zero. So I kind of mentioned all of that in my answer. I've mentioned this idea that yes, work must be done because the potential at P will be positive. It means that we're moving, it will be positive. So I've mentioned that the potential will be positive. It means that we're moving a positive charge like a proton. We would have to do work to overcome repulsion it, moving it from infinity to P. So moving it from outside the field to that point there, I would have to overcome all that repulsion to try and put it there. So yes, I'm going to have to do work. Okay. A small rubber ball containing, this is the last part of this question, so a small rubber ball containing conductive material paint carries a positive charge. The ball is suspended in equilibrium from a vertical wall by an uncharged, non-conducting thread. So the thread will not do any conduction or anything weird like that, so there's not a circuit flowing. The wall is positively charged and produces a horizontal electric field perpendicular to all along the length. It shows that the thread makes an angle at 30 degrees of walls. I then break the thread, explain the motion of the ball. So they're giving you all this information and then you think to yourself, I'm going to do some maths. No, it's explain what's going to happen here. So explain what happens when this ball threads. Well, what's going to happen here is that this ball is going to have, not only is it going to have an acceleration downwards, it's also going to have an acceleration that way. So it's going to have a motion both down and so vertically and horizontally. So we'll move in projectile motion. So explaining the motion of the ball, it is projectile motion. Okay. Because, so it's projectile motion because the ball will have motion in both the horizontal and vertical axes, which leads to a parabolic, and remember that is what's happening at parabolic motion as it falls down. Okay, so basically it will move in projectile motion. It won't be fully parabolic, okay? So it might be wrong for me to say that because, well, actually no, the acceleration in this direction will be the acceleration in this direction is constant and the acceleration down is constant. In assuming this situation, they haven't told me that there's another play or that field gets weaker. It's a uniform electric field, so the field strength is going to be the same infinitely until they tell me otherwise. So in this situation with the information I have, I know it's going to be accelerating this way and it's also going to be accelerating downwards. Okay, so therefore it's going to have this sort of parabolic motion as it happens. Okay, so if we actually look at this mark scheme here, so the ball experiences both vertical and horizontal force acceleration. The ball is giving constant acceleration. The motion is in a straight line. The motion is 30 degrees on here. Okay, so they're being a little bit more specific. They're saying the ball is given, so they're saying that the motion is in a straight line. The motion is at 30 degrees from horizontal to the wall. Okay, so this is interesting because I said I've mentioned experience both vertical and horizontal forces and accelerations, okay? And they've mentioned that the motion is in a straight line, which kind of makes sense, but you're assuming that it's accelerating this way, so I'll have a resulting acceleration this way, which does make sense. And the second mark we're going to, if you go horizontal, needs to be accompanied in some way that the implication it is away from the wall. This may be some repulsion from the wall. Rule again implies straight. Moving away does not imply straight. Okay, so my answer here of saying parabolic is a little bit incorrect, and I kind of actually understand why, but I can also understand why I put parabolic. So let's actually go towards what the mark scheme is saying here and actually divulge into that answer here. So I was correct in saying explain the motion of the ball. Now I understand. So what's actually saying in here is that this point here, the object is in equilibrium. Okay, I didn't unpick that. So let's actually unpick why that answer is not parabolic in projectile. So my answer of saying that there would be a motion, so the experiences motion or acceleration in both the x and y axis. Okay, so that was correct. What I'm saying here will experience both, and it will move both horizontally and down at the same time. Okay, but what I didn't pick up on, and shame on me for not realizing that, and I can see why I went the route I did. The whole point of this sort of 24 days is to answer exam questions and unpick the answers. So what's actually happened here is that this is all in equilibrium. Okay, so it means that if you actually pull down, so we're actually going to tension, and that's 30. So I know that T cos 30 equals mg, okay, and T sine 30 equals ma, okay. So we can actually delete those from each other. So I can do sine over cos, so I can do T sine 30 over T cos 30. So I end up with tan 30 equals A over G. Okay, so because it is at an angle, it means that the relationship between those two are the same, because G is going to be constant and so is A. Okay, so what actually that means there, because we are at equilibrium at this point here, when you break the thread to do that, it's going to move with a resultant in this direction. Okay, this is the resultant, the resultant acceleration. Newton's third law. So if you're going to break the tension there, it's going to cause a force going in the opposite direction. So this is where my resultant acceleration is going to be ending up going in that direction there. So it's literally you got A times G. So when it breaks, we're going to see a force. That's where the motion of these two are going to go there. Bit of an odd question, and I can see why I said parabolic immediately. I think I've got my mind set on another parabolic question that we've done here. So this idea that experience of motion, acceleration, and y and x, and then it will move in line with the thread at 30 degrees downwards. Okay, because A and G are constant, therefore those two are not going to change. And that's kind of bringing back what I said earlier, that A is not going to change. So if the acceleration in G, that relationship between them is not going to change. If I actually do that here, I've got A here, I've got G here, which means the motion for the resultant is going to be going that way there. Okay, so that's actually what's going to happen. This is the resultant acceleration after the tension has broken, okay, because that is the direction of the resultant force between the force pulling this way and the force going that way. So my idea initially of projectile motion is incorrect, and I think that was because I was initially thinking of parallel plates with things dropping down like that. What I didn't realise at this point, when it's out like this, it's already at equilibrium. So this is all at equilibrium. This is a point where it's gone as far out, got G and A in your tension. When you break the thing, at that point when it breaks, the resultant force would be going in this direction, which means that A and G being both constant at that point would mean that it would move down diagonally. So that was just my mistake there. But a good learning point there to actually pick up going, you know what? I thought parabolic because I was thinking of parallel plates. But you know what? Actually, I'm picking the mark scheme. Why is that? Let's have a look at that. Okay. So doing past paper questions is one of the best ways of revising, and because you can actually see the mindset of the examiner and what the kind of things they can ask you. The more you do these kinds of questions, you can actually pick up what's actually going on. All right. So there we have it. That was day 24 of the 24 and the last day of the 24-day extravaganza. Hopefully you enjoyed. And if you've done all these questions, you would have done a grand total of 248 questions, past paper exam questions, or 248 marks worth of them. Okay. Take care of yourself, and I'll see you guys soon.